Okay, we have, boom, 8 in 5, lesson 1, the concept of a function. Let's have some fun today. This is not a highly mathematical, big, long problem set kind of lesson. This is kind of, we're just going to introduce to you these concepts, and really the building blocks are just having paid attention. If you've paid attention over the last over the last year, you should, a lot of the terms and a lot of the concepts that we talk about today, T-charts, graphs, linear functions, these are terms that we're going to pull together, and we're going to try and talk a little bit more specifically about this word function and what it means. This is something we're going to get a little bit more formal with as the lessons go by, but today we're just going to talk about a few examples, two in particular, one that we've done before with linear functions, and then we're going to do a nonlinear function and see if we can understand a little bit better about what these things are and how they and why they matter. So let's go over to our sketch pad, and we're only going to have 3 slides today. And on the first slide, I'm going to try and put the concept of a function to you in 3 different ways, and then I'm going to give you 2 examples. Then we'll do 2 more slides with more examples. So the idea of a function, and again, we've been doing these. We've been doing linear functions, but what specifically is a function? A function is a mathematical construct that you put a value in I don't like those quotes. Put a value in and get a value out. Again, we're not getting too formal with our definitions today. So in other words, if I take this magic function, this is going to be called my function cloud, if you will, function. And hopefully, if this doesn't make sense to you, just throw it away. But if I put this, these will be my inputs. If I put like I put in a 1, this would be my input. This is my input side. And I go through my function cloud, and I might get out a 3. I might put in, these are my inputs. I might put in a 4 and get out a 5. But the idea, and I could put in a 5 and get out a 3. So the idea is for anything, the idea here is that for any number you put in, you get out a number. And it's always the same number. It's always the same number. Okay, so that's kind of the first way. That's kind of like the first piece, A. I'm already kind of using too many colors, maybe. Okay, another way to look at it is B. If you use a T-chart, and this is the same thing that I just said, but in a T-chart, if I put an input, we often call that X, we'll get an output, Y. So here, if I use these examples here, if I put a 1 in, I would get a 3 out. If I put a 4 in, I'd get a 5 out. And if I put a 5 in, I'd get a 3 out. And the idea here is that you cannot have no duplicates, no dupes. No duplicates for my inputs. This will make more sense maybe as we go along, but there's no duplicates for my inputs. My outputs can have duplicates. Some of you may have noticed that we had a 3 here and a 3 here, and that's okay. We can have duplicates for outputs. Okay. So anything we can be represented by a t-chart is indeed a function. And remember, we used all of our linear functions. You know, we had linear functions that looked like this. We had linear functions that looked like this. All of these linear functions were indeed functions because we could represent them in t-charts without duplicating x values. We put in one x value, we get out a y value. Now, the C, this is something where it may not make sense to you yet, but it's the same. It's basically saying the same thing as A and B. And this is the idea of the vertical line test. So the idea is if I have, let's just switch colors. Let's switch colors. If I have my graph and I have a line that goes like, let's make it a different color. So if I have a line like this, the question is this a function? And the answer will be yes, if I can make a vertical line. If for every vertical line I draw, I only hit the line once. Right? Is this a function? The answer is yes, if for any vertical line I draw, I only hit the line once at most. Okay? So an example, so this here is a function because every time I draw a vertical line, I only hit my function line once. An example of a line that would not be, this would be a function. Yes, this is a function. This one here, which I'm about to draw, will not be a function because watch. If I go like this and then I come back, this is not a function because even though I can draw a vertical line here and a vertical line here, if I draw a vertical line, what happens? I cross it 3 times. So this is not a function because a vertical line can be drawn that intersects function more than one time. Right? Greater than one, more than one time. So this here is no. Right? This line here is not a function. Okay, so the vertical line test is just, if this doesn't make sense to you, you can ignore it. It's kind of the graph. Remember how we always said you can do things algebraically with a t-chart and also graphically. This is just the graphical version of A and B, right? We have our A and our B. Our graphical version is the vertical line test. Okay, so let's get a little bit more specific with these functions. And let's talk about a function. We're going to talk about 2 functions. On the first screen, we're going to talk about a function that you already know. Okay, what is this? This is straight out of 8 and 4. This is a linear function. This is a linear function. So we use this word linear function and linear relationship all over the place. But a linear function is simply a function with a constant slope. A linear function is simply a function, and you can write function fn, function with a constant slope. Okay, linear function. So a car traveling at a constant 60 miles per hour. So let's recall from 8 and 4 what this means. If we have a constant, I'm just going to rewrite this, a constant at a constant 60 miles per hour. So remember, miles per hour, that's our hint that this is a rate. This miles, this units per unit. This is our hint that this is a rate. And remember that rates equal slopes. Rates can equal slopes. And the units are our y units over our x units, right? So our y units is miles per hour, and miles per hour is our rate. So that means that our slope should be 60. And so we can model this, right? Y equals mx plus b. Our m is 60 and our b is 0. Don't forget that unit 8 and 4. That's one of the most important units you'll ever learn in math. So if our slope is 60, then we should be able to come back here to our t chart, and we should be able to say, well, after 1, you're at 60. After 2 hours, you're at 120. After 3, you're at 180. And after 10, you're at, if I plug 10 in here, I'm at 600. Which makes sense because here's my 10 comma 600. So it's all looking good. 1 comma, that's about 60, 2 comma about 120, 3, 180. It's all looking pretty good here. And now recall, this is a constant rate. So we should be able to do a couple things. Well, first of all, let's just make sure that we have our definition of function down and everything works. We put a value in and we get a value out. Well, if our function here is y equals 60, x, our in value is our x. Remember, in is on the right and out is on the left. We put in a 0 for x, and if we 0 for x, we get out a 0 for y. If we put a 1 in for x, we get out a 60 for y. If we put a 2 in for x, we get out a 120. There's no duplicates. Of our input. Any input gives us exactly one output. So that satisfies put in a value, get out a value. We can put it in a t-chart with no duplicates. And then finally, our vertical line test. Let's try our vertical line test. Anywhere we draw a vertical line, and so 3, yes. All vertical lines cross function no more than once. And that may seem obvious to you, and that's good if it is obvious. But these linear functions are indeed functions by all 3 definitions of functions. Okay, now one more thing I want to talk to you about, and this is in this unit, and it'll be easy on this. It'll be easy on this example here, and then but we're going to need to tweak it a little bit or look a little closer on the next slide. So let's make sure we really get it. So our average speed, we can look at our average speed between any 2 points. Average, I'm just going to write this AVG from hour 1 to hour 2, and then we'll do from hour 2 to 3, and then from hour 3 to 4. So I need to put 4 on here and put 240. Okay, so the way we find our average speed from hour 1 to hour 2 is we're going to take the points at hour 1. This is our point at hour 1, and then we're going to find the slope from hour 1 to hour 2. And remember, slopes, at least on this graph, are where they're represented in miles per hour, will be our speed in miles per hour. Slopes are our y units divided by our x units, and so in this case, miles per hour. So we can use our slope formula to find our slope, and that will be our average speed. Now we know what the answer to this is because we did it over and over in 8 and 4. But I just want to do the math because on the next example, you're going to see something interesting. So let's switch colors here just so we can see the math separate from the instruction. So we're going to say our m is equal to y2 minus y1 over x2 minus x1. And so that equals y2 minus y1 is 120 minus 60 over 2 minus 1. So that's 60 over 1, and that's 60. And we expect that to be our speed, right? Because our speed is a constant 60 miles per hour. So we expect that our average speed is going to be 60. And it should be 60 for the next one, but let's do it again. So from 3 to 2, we get our y2 minus y1 is 180 minus 120 over 3 minus 2, and that's 60 over 1, which is equal to 60. And then from hour 3 to 4 is the same thing, 240 minus 180 over 4 minus 3 equals 60 over 1 equals 60. And if we want to do it from the whole distance, from say 0 all the way to hour 4, we should still get the same distance because the slope of this line should still be the same. But let's do this from hour 0 to 4. And so we get m equals y2 minus y1 over x2 minus x1. And that's 240 from hour 4 minus 0 at hour 0 over 4 minus 0 equals 240 over 4 equals 60. Okay, so two things that we're really focusing on in this chapter is what is a function, but also we're going to talk about these average speeds and these average rates, these average slopes. And now we're going to go to an example that you've never seen before, and this is just, this is the whole idea of the work that you did in class today, or most of the examples are examples like this one. So be extra careful, and we're going to do all the same math that we just did, but we're going to talk about a different example. Okay, now this boy is throwing a ball. So here's my boy. And he throws the ball straight up in the air, or almost straight up in the air. Ball thrown up in the air. And what we're going to do is we're going to figure out where the ball is at each second that he threw it, okay? So at time 0, the ball's in his hand. Let's call that right on the ground, okay? Now after 1 second, it is 9 feet in the air. Okay, And now think about what happens is the ball goes up in the air. It slows down a little bit, right? Because gravity starts pulling it back to Earth. So a ball doesn't keep going fast, 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 fast if you throw it in the air. It starts to slow down. It slows down. So at 2 seconds, it's at, say, 16. And at 3 seconds, it's at 21. And after 4 seconds, it keeps slowing down, and it's now only at 24. And finally, at 5 seconds up, it stops 25 feet up in the air. And this is a hypothetical example. This might not be exactly how balls fly, but this is close to the same, at least the right shape. Okay. So now it's stopped, right? Because it gets to the top. Once the ball gets high enough and it can't go up anymore, it starts to come back down. So now after 6 seconds, it's back down, and now it's at 24 feet after 6 seconds. And then after 7 seconds, it starts to speed up. 21 feet, and now after 8 seconds, it's at 16 feet, and after 9 seconds, it's at 9 feet, and after 10 seconds, it falls back to the ground. So it's fast, slower, 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 stop, slower, faster, 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 and then it hits the ground pretty fast again. Okay, so this is our T-chart. Now, let's ask a few questions about the T-chart. First of all, is there any duplicates on my input? And the answer is no duplicates. No duplicates on my input. And let's see. So let's go ahead and graph this. And so we'll figure out how high this ball is. Now remember, this isn't the flight of the ball. This does not represent this does not represent the flight path of the ball, right? I didn't throw the ball out and it went over and went down. I threw the ball, up in the air, and then it came back down. But what this does is it represents the height of the ball versus the time in seconds. This is not distance. This is how much time. So after 0 seconds, the ball's at 0. After 1 second, the ball's right here at 9. After 2, it's at 16. After 3, it's at 21. After 4, 24. 5, 25. See, here's my points. And all the same points that are sitting over there on the, on my T-chart. Okay. So there's no duplicates. Any number I put in, at least between 0 and 10. Now this is another point. Now functions don't have to have, you don't have to put in any, you can have limits. It's okay for there to be limits. Okay to have limits on inputs. Okay. And here my inputs are limited between x is less than or equal to 0 and is less than or equal to 10. So my x is between 0 and 10. And that's okay. But if that's my limit, that for any x between 0 and 10 that I put in, I should be able to get out an output. Now notice what's interesting on this output. It's interesting to notice that I have duplicates on my outputs. And that's okay. There's no problem with duplicate outputs. No duplicates, but duplicate outputs are okay. No duplicates for inputs. All right. Now what's the third thing? So any number we put in, we get one out for between 0 and 10. That's our domain, or our input. Domain is an interesting word. Domain is your input values. It's another word. domain is another word for inputs. I can put things in a T-chart and have no duplicates. That's B. And then for C, any line that I draw, any vertical line, I will not hit the function more than one time. So we pass the vertical line test. Okay. There we have it. So the interesting thing about this graph is let's go back to 8 and 4 for a second, and let's ask ourselves some questions. This is not a linear function. This is not a linear function. And why not? It is not a linear function, A, because the graph is not a straight line. Graph is not a straight line. Okay. Now B, I'm going to show you something real quick, and it's that this function is modeled by this equation. So this is my algebraic representation of this graph. And so the key is because, and remember what we said about linear functions. If they're written algebraically, your y and x's can't have, these exponents that are greater than 1 on them. And I have this exponent of 2. And so I know it's not a linear function because my x has an exponent that is not a 1. Okay, and I just told you that. You don't worry about functions that look like this. We're not going to do too much with them, at least not right now. I just showed it to you to show you that the graph to just teach you what we've been saying all along through 8 and 4, that graphs or equations that have exponents that are not 1 are going to give you non-straight lines, so non-linear functions. But this is indeed a function. It is a function, but not a linear function. Okay, let's just take a break, just take a breath, and I'm going to do one last thing over here on the right. Yeah. So now this ball is not flying at a constant speed, right? Because it's fast down here and it slows down and then it speeds up and starts coming down. So we know it is not a constant speed. Right? If it was a constant speed, we'd have a straight line, we'd have a flat slope. But because this is not a straight line, it is not a linear function, it is a curved graph, the ball is going at different speeds, we know that we are going to get some different average speeds when we look at it. So let's look at the average speed between various intervals. Average speed from 0 to 1 second. Let's look at the average speed from 3 to 4. Let's look at the average speed from then from 6 to 7. And then how about from 9 to 10? Okay, we're going to do all of those average speeds. And let's see what happens. Now, remember, we expect it to be going fast here, slower here, and then again to be faster over here, right? That's what would happen if we threw our ball straight up and then it came back down. It'd be faster at the bottom. So let's see if that's what happens. So how are we going to find our average speed? We're going to use our slope formula. We can still use the slope formula. So we're going to estimate our speed by finding that slope. We're going to find our slope between 3 and 4. We're going to use a slope between 6 and 7. And then we're going to use one from 9 to 10. And we're going to calculate all of these slopes and see what happens. Again, we expect it to be fast, slow, slower, but then again faster. So let's see, from 0 to 1, m equals y2 minus y1 over x2 minus x1. So y2 is, we're going to look at these two right here, 9 minus 0 over 1 minus 0. And so that's 9 feet per second. All right, from 3 to 4, here we go, right here. Let's switch colors just because it will make it easier to see. I should have done that here. 3 to 4, 24 minus 21 over 4 minus 3 equals 3 over 1 equals 3 feet per second. And that makes sense. It's slower. It's faster here. Here it's 9. Here it's 3. Now let's look and see what happens between 6 and 7. Well, we're here. And I've got to do 21 minus 24 over 7 minus 6. And here I get negative 3 over 1, or negative 3 feet per second. Whoa, what is going on with this negative? Negative. Here it was positive, and here it's negative. Positive 3, here it's negative 3. And let's do 9 to 10. So 9 to 10 is 0. Here's my 0 minus 9 over 10 minus 9. So that equals negative 9 over 1, which is negative 9 feet per second. Whoa. So what's the difference? Here I got negative, and here I got, this is positive 3. So I have positive 9, positive. These are both positive, and these are both negative. Wow. Well, let's see. Let's think about this. Well, going up, we had maybe positive means we're going up, and negative means we're going down, and that would make sense. So we're at a fast 9 feet per second, then we slow to 3. We come to a stop here at 0, and now we start to pick up speed but now we're going minus 3, which means we're going down 3 feet per second. And then here we're at negative 9 feet per second. So let's give ourselves a little happy cat here, right there in the middle. And let's talk about, let's kind of summarize what it is that we've learned. Okay? We've learned 3 things. We've learned 3 things today, and let's just write those things down. 3 things we learned. 1, functions. You get 1 input, but for each input, you get 1 output. You cannot have duplicate inputs. but you can have duplicate outputs. Another way of saying that is there's no duplicates on left side of t-chart. And another way of saying it, and maybe it's hard to figure out why, but is it that you must pass the vertical line test. Okay, the second thing we learned is that not all functions are linear. Not all functions are linear, some are. And these have constant rates. If not linear, the rates change. And 3, you can find the average rate between any 2 points by using the slope formula. M equals, well, I'm not going to say M, I'm going to say the average rate of change equals y2 minus y1 over x2 minus x1, which is our slope formula. And so this is, you're going to have some questions on the homework where you have to find some average rate between 2 points. One other thing, and this is I guess your homework help. I want to go back to one thing here, and I'm going to look at this graph. And let's look at this graph. And what does this represent? Remember, this point here represents the start of the ball's path. And likewise, what does this represent? The end of ball's path. Right? In 10 seconds, it's come back and hit the ground. So hopefully this was a fun lesson. You got it. It's an introductory lesson. The homework is only one problem, I think, with a few subparts. We'll get back to some more rigorous math maybe in lesson 2, and we're going to get all the way through lesson 14 and 8 and 5. And we will see you with lesson 2 very soon. You're welcome. We'll talk to you next time.